Dear listeners of ciel, ouvert, I reassure you, this won't happen. However, the ISS will indeed crash to Earth in 2030. Why is that? Since 1975, the USA, Russia, and other countries have collaborated in space, leading to the creation of the ISS in 1998. However, the ISS is aging rapidly and countries no longer want to maintain it. Are we witnessing the end of international space collaboration? Here is how. If one has to answer the question, is this the end of international space collaboration? This would mean that countries are currently collaborating on space exploration. But when did it all start? Imagine this. It's 1972. Just 3 years ago, the first human to walk on the moon was American. You've beaten your archenemy, the USSR. And now, your latest space program, Apollo 17, has just come to an end. You're left with thousands of aerospace engineers and billions of dollars worth of infrastructure in your hands. And even though you do no longer need them because you've won the race. All of this, and even the entire world, could go up in smoke if nuclear war were to break out. Then, suddenly, an idea hits you. What if, instead of being a tool for competition and rising tensions between nations, space exploration could become a way to support collaboration and ease global conflicts? It was in this context that the USSR and the US decided to carry out the first international space collaboration, the project Apollo-Soyuz. The idea, simple on the surface, was in reality as complex as it was ambitious. The goal was to dock a Russian Soyuz 19 spacecraft with an American Apollo in space. And while it's obviously harder to meet up in orbit than at the local mall, the real challenge was agreeing on standards between two entirely different sets of Russian and American systems. Here is a list of just some of the things they had to agree on. The measurement system. Of course, the American being, well, American, they use a completely different system than the metric one, which made communications way more complicated. Imagine the Russians designing a docking port 2 meters wide, while the Americans make one that's 2 inches wide. Good luck with that rendezvous. And it's not just length. Pressure, Russians use pascals, Americans use psi. Weight, kilograms and pounds. The list goes on. Thankfully, the Americans eventually converted all their measurements to metric. And according to astronaut Chris Hadfield, they made the right call. In his book, An Astronaut's Guide to Life on Earth, 2013, he writes, "On the ISS, we measure everything in metric. It's the only system that makes sense when you're working with international crews." They also had to agree on the air the astronaut would breathe. The Russians use a high-pressure mixed gas atmosphere, while the Americans breathe low pressure, pure oxygen. Each system worked fine on its own, but switching from one to another could be deadly, causing decompression sickness with nitrogen bubbles forming in the bloodstream. Language was another major issue, of course. They had to bring 2 translators on board just to ensure nothing got lost in translation. But my favorite anecdote is about the shape of the docking systems. Let me explain. The Russians use a hermaphroditic docking system where both ports were symmetrical with the same function, while the Americans use a male-female system. The system chosen was the Russian one because it was more versatile. Indeed, if there was a technical problem with a sex port, docking was generally impossible, whereas with a hermaphroditic port, Docking was usually possible because both ports had the same role, rather than one being passive and the other active. Additionally, any hermaphroditic port can be docked with another, whereas it's impossible to dock a male port with another male port. But most importantly, choosing a male-female system meant that one of the two countries, the US or Russia, would have to play the role of the female, which was unacceptable for both countries. Sometimes we don't realize the huge impact such a detail can have. But perhaps it's for the best, as hermaphroditic ports are objectively better, though they are more complex, heavier, and expensive. These were therefore examples of issues on which the Americans and the Soviets disagreed. However, the Apollo-Soyuz project did indeed come to life. This implies that both sides were able to overcome their differences and work together to build something that would soar higher than any Tower of Babel. From then on, international space collaboration would continue to develop. While cooperation between the two sides worked well during the 70s and the 80s, it was after the fall of the USSR in 1991 that both countries sped up the process of merging their space stations. In 1993, they signed what is called the Agreement between the United States of America and the Russian Federation concerning cooperation in the exploration and use of outer space for peaceful purposes. More concretely, the American space station Freedom and the Soviet Mir-2 were merged into a single station. Some saw this as the triumph of global peace over geopolitical tensions. In reality, Mir-2 was a more modern version of the original station, and although it was meant to replace it, it was also about to be abandoned due to the lack of funding. So the Soviets found a way to make use of what they were about to throw away in order to strengthen their relationship with the Americans. Now that mechanical unification was made possible, it remained to be seen whether astronauts and cosmonauts could actually live and work together. This was tested between 1995 and 1998. Several American astronauts spent months on board the remaining Russian station, Mir. The goal was to develop both technical and linguistic cooperation that would be useful on the joint station. One notable example is the American astronaut Shannon Lucid, who spent 188 days aboard Mir. Since collaboration had now become possible, in 1998, the Americans decided to add the Unity module and the Russians added the Zarya module, which, by the way, means dawn. Once assembled with Mir and Freedom, these modules gave birth to what is now known as the ISS. Later on, the Europeans added the Columbus module in 1928, which serves as a laboratory. The Japanese added the Kibo module in 1929, designed for experiments carried out in the vacuum of space. The Canadians contributed to the Canadarm, a robotic arm used for maintenance, and so on. Ultimately, the justification for all those investments, namely scientific research, is fully shared among all participating countries. A good example is the NASA Twin Studies, which provided valuable data on the effects of long-duration spaceflight. And even during recent tension between the US and Russia, the schedule for station command or the rotation of supply shuttles has remained unchanged, a clear sign of the strength of international space relations. So, it's clear by now that the ISS is an incredible tool and that all participating countries are satisfied with working together on it. However, it's also necessary to assess the current state of the ISS. The station was built at the end of the 20th century using the most advanced technologies of that time. Unfortunately, those technologies have aged poorly. One major issue is that virtually none of the systems from that era work wirelessly, which makes it very difficult to connect modern devices with older but still vital systems. Of course, repairs have been made over the years, but the station has far exceeded its intended lifespan. It was originally designed to last 10 to 15 years, and yet we are in 2025 celebrating its 27th anniversary, almost twice that. While maintaining the station is still technically possible, it's extremely costly and doesn't allow the development of new features, which is a serious drawback at a time when space agencies are setting their sights on Mars. According to NASA, the ISS costs the United States $3.1 billion per year, and additional $2 billion is covered by the other partner countries. Even though the station's operation lifespan has been extended, there will eventually be a failure that cannot be repaired, rendering the ISS unusable. For example, gas leaks were detected in the Zvezda module in 2022, and despite several repairs attempts, they could not be fully resolved. Following this, NASA initially considered ending its operations on the ISS in 2024, before reaching an agreement with Russia to continue until 2030, the year by which Russia plans to detach its modules in order to relaunch its own national space program. It's clear that the ISS must eventually be retired, but how is the decommissioning of a space station managed? Until 2028, nothing special happens. After that, some modules and equipment will be retrieved by their owners, mainly the modules belonging to the Russian space agency Roscosmos. Once the detachable Russian modules are gone, private company modules will be attached to what remains of the ISS to prepare for their operation as commercial space stations. These new private modules are initiative from the American company Axiom Space and the European company Starlab. Finally, by 2030, when all recoverable equipment has been removed from what is left of the ISS, the process of destroying the station can begin. If you're wondering whether it's possible to simply let the station drift in space, that is strictly impossible, because it could then collide with other stations or crucial satellites. No one would be able to control its trajectory. To properly destroy the station in the atmosphere, it cannot be going too fast, otherwise debris wouldn't have enough time to burn up completely from atmospheric friction. To ensure this, the station must first be lowered from about 400 kilometers altitude down to 200 kilometers in a controlled descent. It's then that its crash can be triggered in a safe, uninhabited area, Point Nemo. The remains will then join what's left of its predecessor, the Mir 1 station. Even though the ISS era is coming to an end, humanity will not give up on exploring and exploiting space. That's why many new space programs are already in place to succeed the ISS. I've already mentioned several Western private companies, Starlab, Axiom Space, and Blue Origin, which aim to develop stations for scientific, touristic, and commercial missions. Regarding the commercial aspects, these companies are trying to attract investors by highlighting products such as ZB LAN optical fibers, which have been produced aboard the ISS, Since there is no gravity during their creations, problems like density fluctuations are avoided, resulting in high-quality fibers that reduce signal loss for infrared wave transmissions. There are also national programs such as ROS for Russia and Tiangong for China. These projects also have scientific objectives, but I would say less commercial ones. Let me quote statements from the Russian and Chinese space agencies. The future autonomous Chinese space station will be dedicated to scientific research, technology, and the demonstration of national capability in human space flight. The Russian space station will be devoted to research, support for Russian crewed missions, and national space sovereignty. Finally, the two main multinational programs that will remain are the Gateway program, which brings together Western nations and Japan with the goal of preparing lunar and deep space missions, and the ILRS, International Lunar Research Station, which will enable lunar exploration by joint Chinese and Russian teams. The upcoming retirement of the ISS undeniably marks the end of a unique model of global space cooperation. As a true symbol of dialogue between former Cold War rivals, the International Space Station has since 1998 brought together the United States, Russia, Europe, Canada, and Japan around a shared technical, scientific, and political project. But this model, based on the close integration of modules, budgets, and crews from several continents, now appears to be nearing extinctions. The ISS successors, whether commercial, national, or lunar, are fragmenting the space landscape. On one side, Western programs, American private stations, the Gateway, continue a targeted and structured form of cooperation, though not one that includes all major players. On the other, Russian-Chinese initiative, ROS, ILRS, reflect a pivot towards geopolitically aligned partnerships. To put in a nutshell, collaboration remains international, but is no longer global. It is becoming polarized in a path along shared interests and values. We are moving from a shared space between former adversaries to a segmented one between allies. This doesn't mean the end of the dialogue in space, but rather its reinventions, more modular, more competitive, more commercial, and above all, less unified than in the ISS era. Thank you for your listening.